Okay. Welcome back, everyone. Let's get started. Uh, this is week 9 of the discussion sessions, and we will begin from where we left in the previous week. So, just doing a quick, you know, recap of what we did in the previous week. So, we are interested in. So, we were basically looking into the creeping flow equations, if you remember, uh, which we saw that they were linear, and the inertia term basically dropped out when we consider the fact that the Reynolds number Reynolds number basically goes to zero. And then we essentially saw that if we have a 2D problem, we can effectively use something which is known as the stream function, and then develop an equation for which the stream function satisfies. And then we saw that the stream function basically satisfies the biharmonic equation for a flow that is planar or axisymmetric. And then we argued that in spherical coordinate, this biharmonic operator basically looks something like this, which has as you can see, it has a dependence on r and theta. And here, instead of directly using theta, we use a transformation which is just eta, which is just cosine of theta basically. So in a way, this uh, axisymmetry in spherical coordinate so it basically denotes that my variables are a function of r and they're a function of eta. This is what the definition of axisymmetry in spherical coordinate says us. Okay. And then using this stream function, we solve the problem, which is similar but little bit more involved than the problem that you solved in the theory classes. So remember, what you did is in in the lecture classes, you saw that you basically found out something which is known as the Stokes drag. That is the drag that a spherical particle would experience when it is subjected to a uniform flow in the creeping flow limit. And then what we said is that in this problem, instead of the spherical particle being held stationary, it is moving due to the presence of a background parabolic flow. It is basically moving with an unknown velocity u. This u is the non-dimensional velocity of the sphere that we are going to calculate as a part of the problem. And then if you recall, we said that we'll be using, so since this u is an unknown, we need an extra set of equations for u. uh, and for that, what we discussed is that, so there is something as a hydrodynamic force free condition, meaning that the net force on the sphere is equal to zero. That is, the external force that the sphere experiences because of the presence of a background flow is being balanced by the viscous drag that the flow would basically exert on the sphere on account of viscosity. And we hadn't formally established this force free condition yet, but we'll do it today. And then we will see that how using this force free condition, you can basically calculate what is the unknown velocity of the sphere that we are interested in. Okay, so how we proceed the problem is that we wrote all our velocity components in spherical coordinate. That's the first step that we did. And then I said that in for any axisymmetric bodies, uh, that is, for any flow past axisymmetric bodies, if it's a planar on axisymmetric flow, then we all know that the stream function satisfies the biharmonic equation. And using something which is known as the method of eigenfunction expansion, although we haven't explicitly derived this in the last class, but we said that we can use something which is known as method of eigenfunction expansion to formally find out a series solution for psi that basically psi satisfies. And then we said that the task in our hand now is to basically evaluate these constants a n, b n, c n, and d n, which will be reflected partly by the far field. So it will be reflected partly by the far field boundary condition, and the other constants, for instance c n and d n, will be dictated by the boundary condition of the surface of the sphere. So that's the idea. And since it's a series solution of some orthogonal polynomials. We saw that these orthogonal polynomials were nothing but Gegenberg polynomials, which were related to the Legendre polynomials of this form. Okay, so that's how we did. And then the first step was to evaluate the far field form of the stream function. So the first step was to evaluate the far field form of the stream function in once the far field flow is known basically to us, and then use this So I think that's where we did. Just 1 second. So yeah, so basically we know the far field from the velocity, and then from this far field from the velocity, we found out what would be psi infinity just by integrating either the ur or the u theta component of velocity. And then we saw that in fact we use the u theta component of velocity to calculate psi infinity, and then we saw that the modes uh, and something which is known as the orthogonality principle. So using the orthogonality principle, we saw that the modes that are present in psi infinity were the modes n equal to 1 and n equal to 3. And then we argued that the form of the solution of psi that it will satisfy in the entire domain will be dictated by the modes that are present in the far field solution. And this is again a feature of the orthogonal functions, and things will be much more clarified when we formally evaluate the boundary conditions on the surface of the sphere, and then apply the orthogonality principles to check that which modes will be present in the general solution for psi. And then we will eventually see that indeed the modes that is n equal to 1 and 3 is only restored, I mean they are only recovered in the general solution, which were eventually present in the far field solution of psi infinity. Okay, so that's the idea, and that's what we will do today. So so that's what we did in the last class. So I'll stop here for a couple of minutes, and then I'll let you guys to just think about what we did, and then we'll proceed from now on. So if you remember, the objective now is to calculate these is to basically calculate these constants that were cn's and dn's, because psi infinity is already known. And what we did is we wrote that the total stream function is equal to the disturbance stream function, which will be generated because of the presence of the sphere, plus the far field form of the stream function, which is psi infinity, which we already know. And the disturbance from the stream function is now dictated by these constants cn's and dn's, and we will use the boundary condition on the surface of the sphere to calculate these constants cn's and dn's. And we will eventually see that since n equal to 1 and n equal to 3 modes are present in the form of psi infinity, because of the fact that these qn's are orthogonal, we'll also have just C1, C3, and D1, D3 in the disturbance stream function, and we will see that very shortly. And that's the part of that's the only part of the solution that is left. And yeah, after that we will use a theorem to this theorem basically establishes the force-free constraint that we discussed some time back. And then we will use this theorem to basically calculate what will be the unknown velocity of the sphere, and that's the objective. That's the final objective of our analysis. Okay. So yeah, so I'll stop here for a couple of minutes. I'll let you guys to think. So we ended this class by stating that we now require to evaluate this constant from the surface of the sphere. Okay, so we'll begin in just 1 or 2 minutes. If you guys have any doubts or like any suggestions, you can let me know. Okay, if no suggestions, let's get started from where we left. That is from this point, that we have established that now the stream function, which is the prime variable of interest, is written as the stream function that is dictated from the far field flow, that is psi infinity, plus the disturbance, which accounts for the fact that there is now a sphere in the undisturbed flow field, and the sphere will impart certain disturbances in the flow field basically. Okay, all right. So what we saw is that the form of stream function, I'll just rewrite it once again, that the psi, and this is the main unknown that we are interested in, which is of course a function of r and eta only, because it's an axisymmetric problem. We have written this as psi infinity, which again is indeed a function of r and eta, plus psi disturbance. And this, so we can write this once again because of the fact that the governing equations are essentially linear. Okay, and that's the reason why we can decompose this psi into psi infinity and psi disturbance. Okay, and of course the psi disturbance is also a function of r and eta. And the psi infinity, we have already evaluated this, so this is something like this. It is 2 by 5 r power 4 minus 1 minus of capital U, which is the unknown velocity of the sphere we are yet to find out, times r square. Okay, and then this is q1 of eta, that is the first mode of the Gegenberg polynomials, and then this is minus of 2 by 5 r power 4 q2 of eta, okay, plus the disturbance. So the disturbance is of the form summation n equal to 1 to infinity. It is Cn times r power 2 minus n plus dn times r power minus n. Okay, so that's basically, and this is qn of eta. Okay, so this is basically our psi disturbance. Okay, so before using the boundary condition of the sphere and the orthogonality principle to see that which modes of Cn's and Dn's are present, I will quickly highlight a note here. Before going into finding the writing, before going into writing the boundary conditions and the other things, I'll quickly highlight a note here, and I believe it will be useful for you when you deal with these kind of problems. Okay, so the fact is that if you closely see the form of psi disturbance, so psi disturbance is what? It is nothing but summation n equal to 1 to infinity. That is just this term that I'm writing it once again, just for the sake of explaining you guys. Okay, so it is just summation n equal to 1 to infinity Cn times r power 2 minus n plus dn times r power minus n. Okay, and then this is multiplied with qn of eta. All right, now you can appreciate that if C1 is not equals to 0, okay, then the maximum, then you can think of it something like this, that the maximum possible disturbance that the sphere would impart is reflected by the mode n equal to 1. Okay, because this is because of the fact that if n is 1, I have r here, which is 2 minus 1, which is r, and for all other values for n greater than 1, these terms, so this 2 minus n would basically be that basically will be less than 0, to be precise, for all other values of n which is greater than or equal to, let's say, 2. For n equal to 2, this term will basically drop out, that is it will become r power 0, which is just C2. But for n greater, so for n greater than equal to 2, this term would either be 0 or it will be of the form 1 by r power n minus 2. That I hope you can understand, which means that the maximum possible disturbance that it's like the maximum possible disturbance that the sphere can exert on the fluid is possible when C1 is not equal to 0. Okay, I hope you can argue on the fact that this indeed needs to be satisfied. So in other words, if C1 is not equal to 0, then we can define something which is known as psi d max. Then this is the maximum possible disturbance that the sphere will impart on the fluid, and this should be equal to C1 times r power 2 minus 1, which is just 1. I am not bothered about this term because this term will anyway decay as 1 by r. Okay, that is for the stream function. So for the velocity, it will decay faster than 1 by r square. It's something like this because velocity is always the derivative, which means that this C1 r times Q1, okay, is the maximum possible disturbance stream function that could be generated as a result of the flow. Okay, so based on this maximum maximum value of the stream function, I would say, if I now define something which is known as, so based on this, if I now calculate the corresponding velocities as a result of this psi d max, then I can write that, let's say, ur d max is nothing but minus 1 by r square. That's the relationship between the stream function and the velocity component in spherical coordinates. So it would be del psi d max by del eta. Okay, and then if you calculate, it will simply be C1 by r times P1 of eta, because you need to calculate the derivative of this, which is nothing but just your Legendres. And similarly, if you calculate this u theta d max based on the psi d max, it will be just minus of 1 by r square root of 1 minus eta square del psi d max by del r. And then if you do this calculation, you can see that it just comes out to be equal to minus C1 Q1 by r times square root of 1 minus eta square. Okay. I hope you can understand what I'm trying to say. So you can appreciate that if, you know, if C1 is not equal to 0, then my U, that is UR d max and U theta d max, they decay as 1 by r. Because you can see that UR d max is also proportional to 1 upon r and U theta d max is also proportional to 1 upon r. And the rest all are just order 1 quantities. Okay. So you can now understand that the highest possible disturbance in the velocity field, in the disturbance velocity field, can decay as 1 upon r. Okay. All other disturbances will decay faster than this highest possible disturbance, and this highest possible disturbance has got a name, that these velocity fields has got a name. They are known as Stokes-Slade. They are basically known as Stokes-Slade velocity field. And you can appreciate that Stokes-Slade velocity field only arises when this condition is satisfied, that C1 has to be that C1 is non-zero. Okay, but we will see later on that for a force-free particle, that is, if the net force on the particle is 0, then this C1 has to be equals to 0, and this comes as a constraint which calculates, which gives me the value of U, and we will see this by theorem. Okay, but then you can see that you can then say that if I have a force-free particle, then the Stokes-Slade velocity field is 0, simply because C1 is basically equals to 0. That is true for a force-free particle. But for instance, let's say the Stokes-Drake problem, that's not a force-free particle because it experiences a drag. Then for the, let's say for the Stokes-Drake, the velocity field that you get, they are essentially known as Stokes-Slade velocity field. Okay, that is also because for the Stokes-Drake problem, you just have n equal to 1 mode. So the only velocity field that you get are nothing but this disturbance velocity, which are nothing but the maximum velocities. Okay, so that's the reason why they are known as, you know, Stokes-Slade velocity field, because it borrows the, you know, it borrows from the motivation of it borrows the motivation of the Stokes-Drake problem. Okay, but I hope that now you understand that how does the disturbance velocity field varies, how does the maximum disturbance velocity field varies if I have a condition that C1 is not equals to 0. Okay, but then again, if C1 is equals to 0, then the Stokes-Slade velocity field is equal to 0, and then you can appreciate that the maximum disturbance for a force-free particle will vary as 1 upon r square. Yeah, I mean, yes, it should be 1 upon r square, because your n equal to 1, because your C1 has to be equals to 0, then the only possible scenario that can arise will be from mode equal to 2, basically. Okay. But yeah, that's the idea. Okay. So once again, the point is that if C1 is not equal to 0, then your disturbance velocities will decay as 1 upon r, and this is a very important result in creeping flow problem. In the interest of time, I cannot explain that these Stokes-Slade velocity field is essentially, so it's a very important, you know, so it has got some very important usefulness in creeping flow problem, and you can appreciate that because this is the maximum possible disturbance that will arise in the flow field, and the flow is governed, and the physics of the flow is governed by the maximum possible disturbance, which is just the Stokes-Slade velocity field that we just discussed. Okay, so so that's the quick note that I want to give. This is just a note, and now without any delays, let's now go ahead and calculate these CNs and DNs for our problem. Okay. All right. So the next step. So this is the next step. So what's the number? I think this is what? This is step 3, basically. So the step 3. So the step 3 is to, apply boundary conditions on the surface of the sphere to evaluate CNs and DNs. And once CNs and DNs are known, you can appreciate that you know the entire stream function, meaning that you know everything. Once the stream function is known, you know the velocity field from the relationship between velocity and stream function. And if you insert that into the R momentum equation, you will basically get the pressure, that the variation of pressure along R and eta, basically. So once the stream function is known, it's just a matter of algebra that you know basically everything. You know the velocity, you know pressure, and if you know velocity and pressure, you know stresses and everything else. Okay. All right. So, let's then apply the boundary conditions on the surface of the sphere. So what do we have? So one boundary condition is that if I use the no penetration boundary condition, then I have that my UR, that is the total velocity field at R equal to 1, this is equals to 0. Okay, and then I can write this UR as in terms of the stream function as del psi by del eta. Okay, at R equals to 1, this is 0. That just comes from the relationship between the R component of velocity and the stream function. And now if I use this form of psi, because I know that my psi is equal to what? So my psi as a function of R and eta, this is equal to 2 by 5 R power 4 plus u minus 1 R square. Okay, and then I have q1, which is a function of eta, plus minus 2 by 5 R power 4. So let's just write it as minus, because it is already this minus. So this is minus 2 by 5 R power 4 Q3 of eta. Okay, plus summation n equal to 1 to infinity. Okay, they are just these things. Okay, Cn R power 2 minus n plus Dn R power n. Okay, Cn R power 2 minus n plus Dn R power minus n multiplied by Qn of eta. All right. So now let's use this boundary condition. So then what do we get? So if we use this boundary condition, that is the fact that del psi del psi by del eta is equal to 0, then I have what? Okay, then I have what? So we'll use this boundary condition. Let's name this. Did I name some equations here? Did I number some equations here? So this is equation. Okay, so it's a long thing. So all right, so this is equation 3. The form of psi, let's say I write it as equation 4. This is the far field form of psi, and then okay, and then this combined form of psi, I will name it as 5. Okay, and the combined form of psi segregated with respect to psi infinity as psi disturbance, we'll name it as 5a. Okay, and this is then again 5a, and then we'll name this no penetration boundary condition as equation 6. And then if I substitute this psi into equation 6, what do we get? So we get, so let's just substitute it. So we get 2 by 5 R power 4, because this is just a derivative with respect to eta, so this term will just remain the same. So it is just 2 by 5 R power 4 plus of u minus 1 R square. This term would be, so since this is just derivative with respect to eta, this term would be just dq1 by d eta. But we know that dq1 by d eta is p1 of eta. Because remember, the integration of Legendre is Gegenbaur and the differentiation of Gegenbaur is just Legendre. So this would just be p1 of eta. And then this would be again 2 by minus 2 by 5 r power 4. This would be p3 of eta by the same logic. Okay, and then this would be plus summation n equal to 1 to infinity cn r power 2 minus n plus dn r power minus n times of dqn of eta by d eta is again pn of eta, and this is equal to 0. Okay, that's it. That's the no penetration boundary condition on the surface of the sphere written in terms of the stream function. Okay, all right. So this is again the same equation, that is equation 6. Okay, now here is an important thing, because now what we need to do is we need to look, or we need to evaluate that what are the values of n, that what modes of cn's and dn's will be present in this will be present in order to satisfy this equation. Now you can appreciate that since these Legendres are orthogonal, this means that just from the orthogonality principle, I can argue that only C1, C3, D1, and D3, these modes will survive basically. That is only for n equal to 1 and n equal to 3 modes will survive. And this we have already discussed, that the far field stream function will dictate the number of modes that are present in the general form of stream function, and also the disturbance stream function. Okay, so C1, C3, D1, D3, these are the only non-zero modes. These are the only non-zero modes. So this means that all other modes apart from n equal to 1 and n equal to 3 in the disturbance stream function, they will just go to oblivion. They are just 0 basically. So then, and then again, this is the result of the orthogonality of, this is the result of this basically is a result of orthogonal functions. I mean, they are characteristics of orthogonal functions, and you can appreciate that if I, let's say, for instance, let's say I have a P7 mode, then if I use the orthogonality principle, then I need to multiply this equation by P7, and here it will also be P7, and then if I integrate this, then these terms will basically go up to be equal to 0, which means that P7 modes cannot be present in the solution for your stream function. The reason behind is that since if P7 is present, then your psi infinity basically goes to 0, but this is not possible. Your psi infinity, so your velocity field should approach your u infinity or the stream function psi infinity, which is only possible if I only have n equal to 1 and n equal to 3 modes, because for all other modes apart from n equal to 1 and 3, this integration, if I use the orthogonality principle, that is if I integrate it from -1 to 1, multiplied by m, and then integrate it with respect to d eta, where m is not equal to 1 and 3, this integration basically vanishes. Okay, and that is the reason why I keep on saying, and we always say that the far field stream function will dictate the number of modes that will be present in the disturbance stream function, and this is the maths behind it. The maths behind this argument is nothing, is just the signature of orthogonal functions basically. These are due to the orthogonal, these are due to the behavior of the orthogonal functions. Okay, all right. So now it's easy, right? Because I know that I just have n equal to 1 and n equal to 3 modes, so I can just write down expand this for n equal to 1 and 3, and if I do that, I just have this term. I just have 2 by 5 plus, so I'll combine the n equal to 1 mode together for the far field and the disturbance, so it becomes 2 by 5 plus u minus 1 plus c1 plus d1, and remember that this r will just be 1 now. This r's will just be equal to 1, because we are evaluating this at r equal to 1 to be precise. Okay, so this becomes 2 by 5 plus u minus 1 c1 plus d1, and then I have dq, or then I have what? I have p1 of eta plus I have the third mode, which is minus 2 by 5 plus c3 plus d3 times p3 of eta, and this is equals to 0. Okay, now since the modes of orthogonal functions are independent, that is, they behave independently, then for this to be equals to 0, the only possibility is that these coefficients of the orthogonal functions, they has to be equal to 0 independently, because the modes behave independently. That's the reason. Okay, now since the orthogonal modes are independent of each other. Okay. And now since the orthogonal modes are independent of each other, and I want this, I want this term, I want these two terms basically to be equal to 0. The only possibility that I can have is that the coefficients individually have to be equal to 0. Okay. Which means I have, so therefore, I have two conditions here, 2 by 5 plus q minus 1 plus c1 plus d1. This is equals to 0. And then I have minus 2 by 5 plus c3 plus d3. Okay, this is equal to 0. So I'll name this as, let's say something. How do I name? I'll name this as 7a and 7b. Okay. All right. So that's one boundary condition that we use. And from this, we have two equations which have four unknowns, basically c1, d1, c3, and d3. But we just have two equations. So we are left to use one more boundary conditions, which is nothing but, the usual no slip boundary conditions that comes on the variable u theta. So if I use this, so the second boundary condition is that the second boundary condition on the surface, So this is the no slip, boundary condition, which says that u theta at r equal to 1, this is equals to 0. Okay. See, remember these are zeros because remember the axis was basically moving with the particle basically. So the axis system was moving with the particle. So as in when the particle moves, the axis also moves, meaning that on the surface, if you see it on the surface, that if you see the velocity component with respect to the moving frame of reference, you will see that they are indeed zero basically. Okay. All right. So u theta at r equal to 1 is equals to 0. And then if you relate this with stream function, you will eventually see that del psi by del r at r equal to 1 is equal to 0. But we know that at r equals to, so what we know? We know that psi is basically this. Psi is basically this with the modes n equal to 1 and 3 in cn's and dn's. So if you just use this, you will simply get something like this. Okay, so it will be just the algebra. You can verify it at your end. You will just get 8 by 5 plus 2 times u minus 1 plus c1 minus d1 times q1 plus minus 8 by 5 plus minus c3 minus 3d3 times q3, and this is equals to 0. And then again, using the same logic that these modes behave independently, I can therefore say that 8 by 5 plus 2 u minus 1 plus c1 minus d1 is equal to 0, and minus 8 by 5 minus c3 minus 3d3, this is equals to this is equals to 0. Again, because of the fact that the orthogonal modes behave independently with respect to one another. Okay. So I name this, let's say I name this as equation A, 8, which is the no slip, and these equations are, let's say, 8a and 8b. Okay. So that's it, guys. So we are all set. We just required four things: C1, C2, C1, C3, D1, and D3. We have four equations, two from the no penetration condition, that is two from here, and then we have two equations, two from the no slip boundary condition, which are equation 8a and equation 8b. Now, so four equations, four unknowns, and these are just linear equations. You guys are master of this. You can just evaluate these unknowns: C1, C2, C3, and C1, C3, and D1 and D3. So these are now readily available because four unknowns, and four equations. Okay. I believe you are comfortable at your end to do this math and just solve for this. Okay. What I will now show is that, okay, once you know this, so that means what? You know the entire stream function, because now you know the disturbance field as well. You know that there will be just n equal to 1 and 3 mode in the disturbance field. You know the far field, stream function, which means that once you know these constants, you know psi, basically. Psi is now known. Psi is now known. Okay. So the majority of the problem is just solved because we are asked to solve for the velocity field and psi is known. But remember, one more thing needs to be evaluated, which is the unknown velocity of the sphere. Okay, that is something that we need to evaluate, and we say that we'll be using a theorem, and this is where I will introduce you to the theorem, because the theorem is actually a shortcut, for finding the velocity. A more general way of finding the velocity is that calculate the stream function. Calculate the stream function first. That using this, calculate the calculate your stream function, and then from the stream function calculate your velocity, and from the velocity use the r momentum equation to calculate the pressure, and then once you know the velocity and the pressure, calculate the stresses, because you know that your stress is basically the hydrostatic component, which is the pressure, plus the deviatory component, which are a result of the velocity fields. And once you know the stresses, you can find out the traction vector, integrate the traction vector over the surface of the sphere to get what will be the net force on the sphere. And from this, you will get one equation which you need to equate it to 0 because of the fact that your net force is equal to 0 to get the unknown velocity q. So all these series of steps needs to be equal to done, are needed to be done if you follow a sequential manner to find out the net force on the surface of the sphere, and using the force precondition to basically equate that force to 0 to calculate the unknown u, which is the velocity of the sphere. So we will not do so. This is how a general algorithm can be made to basically calculate the u, which in principle is the more general way of doing it. But we will use a theorem here because the theorem directly gives us what will be the unknown velocity of the particle, uh, without having to calculate all these stresses and pressure and velocity fields and all those things. Okay, so I'll write the theorem here. Okay. So the theorem says that for any problem with psi r comma eta, that is the stream function, expressed as, so if we express psi in its general form, which is basically this, that we saw it in the last class, that is the most general form of psi, which is what, which is your equation 1a, basically this. So if you can express psi in this form, that is equation 1a, so the theorem says, okay, the theorem says that so for any problem with psi r comma eta expressed as equation 1, okay, the force exerted by the fluid on an arbitrary axisymmetric body with its center of mass at x bar equals to 0, meaning that your center of mass lies in the origin, which is of course in the case because our axis was fixed to the particle center, and the center of mass indeed lies at the origin for that sphere. Okay, so the force exerted by the fluid on an arbitrary axisymmetric body with its center of mass at x bar equal to 0 is equal to f z, where z is the axis of symmetry, and this force is equal to 4 pi mu uc lc c1. That's it. So once you solve the four equations that we just saw here, once you solve these two equations and these two equations, all you need to do is just evaluate c1, because from the two equations you will get c1, c3, d1 and d3. All you require is c1 to get what will be the force, what will be the net force on the, in fact, this is not the net force, this is the drag force. So it will just give you what will be the drag force on the surface of the object. Okay. So now, so remember this z is equal to, so this z, this is the axis of symmetry. Okay. Which of course is the z axis in case of a spherically symmetric sphere. So this is the axis of symmetry. and we are evaluating the force in the direction of axis of symmetry. Of course, the force will of course be in the direction of the axis of symmetry, which is again is in the direction of the flow basically, because the problem itself is axis symmetry. So this Z is the axis of symmetry, and then the net drag and the net or in other words, the drag force is just this 4 pi mu UCLC C1. Remember, in the Stokes drag, you can show that your C1 happens to be equal to 3 by 2, and then if you calculate this, you basically get your force as 6 pi mu UC times LC, which is nothing but the Stokes drag that you guys are aware of. Okay. So you can verify this at your end, that follow the same procedure. Follow the same procedure that we did for the Stokes drag problem, and then calculate C1 just how we did. And you will see that your C1 will just come out to be equal to 2 by 3. That's it. Okay. I'll stop here for a couple of minutes. I'll just fill my mug with some water and then I'll come back. Okay. Okay. All right. Sorry for the interruption. So yeah. So what we just now saw is that the theorem says that if you can express psi in the expansion that we just saw, then the force exerted, by the fluid on any axis symmetry. See, the beauty of the theorem is that it need not be a sphere or a body of definite set. This is true. This is universal for any bodies, but it has to be an axisymmetric problem. Okay, and then the force is equal to this form. Now the point is that if my net force is 0, this means that the drag force is balanced by the the that the drag force is basically balanced by the external force, and that means that the sphere now moves with this continuous velocity, moves with a continuous velocity, which is uniform, of course. This means that my Fz is 0. This has to be the case. Okay, and then since all other quantities are non-zero, it means that the force free condition just boils down to the fact that C1 is equals to 0. That's it. So this is nothing but the force. So this condition is known as the hydrodynamic force free condition. Okay. Now, in this given problem, if you just solve this, if you just solve, equations, equation 7a, 7b, 8a and 8b, which are just 4 equations and 4 unknowns, you will see that your C1, that means for our problem, solving 7a, 7b, and 8a and 8b, you can show that out of all the four constants, your C1 comes out to be equal to 3 by 2, 1 minus of u minus 1. Okay. So that's so it just solve the problem, and you will see that your C1 happens to be equal to this. C3 and D1, D3 are immaterial here if you are trying to calculate the unknown u. Because again, the reason is that the force-free condition only requires the fact that your C1 has to be equal to 0. So you can calculate the other constant that will in general give you the stream function. But for evaluating the unknown velocity u, you just require this C1. So if you now equate this C1 to be equal to 0, if you equate this to be equal to 0, what you get? So you basically get that your this means that 3 by 2, 1 minus of u minus 1, this is equals to 0. So you can show that your u will come out to be equal to what? So your u will come out to be equal to 1/3. So this is precisely the velocity at which the sphere would move if it is subjected to a background parabolic flow of the form that we consider in the limit of creeping flow analysis. Okay. So as I said, this is the unknown velocity of the sphere. Okay. Subjected to the given background flow that we just now considered. All right. So that's it. That's all that we require, in this problem. And this finishes the this finishes the discussions on creeping flow. We have solved an extensive problem which involves using something which is known as the hydrodynamic force-free condition, then equating the constant C1 equal to 0 to basically get the unknown velocity of the sphere, which is equal to 1/3. And if you write it dimensionally, then this just becomes your dimensional velocity is equal to 1/3 of the characteristic velocity, okay, which is uc. Now uc can be anything. It can be the maximum of the parabolic flow. It depends on whatever you choose as your characteristic velocity. Okay. So whatever you choose as your characteristic velocity, calculate the 1/3. That will be your dimensional velocity with which the sphere would move, subjected to the given background parabolic flow. Okay. So that's it. That ends the discussion here. I'll stop here for a couple of minutes, and then we will begin by the discussions of this week. And we will start off with something which is known as boundary layer analysis. Okay. But I'll stop here for a couple of minutes, just for you guys to uh, just reflect on what we did. And then we will begin by week 9's contents, which is Laminar boundary layer. And then we will, the theory behind it. We will just quickly brush up on what hydrodynamic boundary layer is, and then and then we will look a problem that involves this analysis of boundary layer. It's a simple problem, but we will solve this here, and that's the agenda for today's discussion, basically. Okay, all right, guys. So let's get started. So I think the previous week's contents were up to boundary layer theories. So you had solved a couple of assignments related to laminar boundary layer, which involve using the Blasius. So you have seen something which is known as the Blasius exact solution given by Blasius to the boundary layer equations. And then you also looked into something which is known as von Karman momentum integral approach, which give you an approximate result of the boundary layer thickness with a fair amount of accuracy with respect to the Blasius's exact solution. And the accuracy of the von Karman approach, as we will see very shortly, is dictated by the choice of the boundary layer that we have. By the Yes, I think it's done. Okay. Yeah. Okay. Sorry once again. I don't know what just happened. So okay. Let's get let's get started. So we were discussing the laminar boundary layer. Just I'm making sure that the recording is still going on. Okay, the recording is still going on. Okay. So yes, I need to present my screen as well. I guess so. Running. Trying to start share screen. Continue. Start podcast. Okay, so I think we are back. Sorry once again for the interruption that we had. I believe the past recordings are somewhere, somewhere being saved in my PC, or else I'm very sorry. These are just what to say electronics error that you can't you can have really a control on. So so once again, okay, so let's get started from where we left. So we saw that. So yeah, so we were about to start the laminar boundary layer analysis, and and as I was saying that in your lecture series, you looked into something which is known as the hydrodynamic boundary layer, where you basically solve the Navier-Stokes equation, which were 2D indeed. And then, there is something which is known as the similarity solution. You use that in the, you use the similarity variable, which involve the variables y and x. And you use all those things. And then you obtain a solution for the boundary layer thickness delta, which came out to be, delta by x. So the Blasius's exact solution, this came out to be equal to delta by x equal to some constant by square root of rex, where it is constant, it was exactly equal to 5 if we use the Blasius's, if you use the Blasius's exact solutions. Okay. See, the objective of the boundary layer theory was that, uh, if you recollect, there was a plate and there was this growth of boundary layer that was taking place that was taking place on account of the fact that there is a disturbance now that the far stream fluid experiences, which was coming with some given velocity u infinity. And suddenly when this far stream fluid noticed that, okay, there is a disturbance on my way, this disturbance is propagated by the property of the fluid, which is viscosity, and as a result of this disturbance that is present in the way of the fluid, there is this growth of this boundary layer, which is typically, once again, because of the fact that the fluid bears its own viscosity. The result is that this boundary layer grows, and we call that at any distance x from the, so this let's say x equal to 0, and let's say the plate length is x equal to L. So this x equal to 0 is known as the leading edge. Okay, this is known as the leading edge, while the x equal to L is called the trailing edge. That is the end of the plate. So you saw that there is this growth of this boundary layer thickness, but that there is this growth of this boundary layer. And then we say that from a distance x from the leading edge, the boundary layer thickness, we call it as delta x. It indeed depends on x. And Blasius, what he did is, the prime objective of all the boundary layer analysis is that people just find out this boundary layer thickness delta. That's it. So uh, once they know this boundary layer thickness delta, uh, that is what they actually care about. Okay. And then Blasius, after solving all those, after solving the the 2D equations using the similarity variable and all those things, what Blasius saw is basically so what Blasius finally found out is a is an expression which governs how your delta essentially varies with x. And then he saw that, okay, if I, so from his similarity approach, he saw that this delta, inherently, is a function of x. This varies as some constant times c by square root of rex. And then you can eventually, if you eventually expand this rex, if you just eventually expand this rex as what, rho times u infinity x by mu, you can eventually show that your delta is proportional to square root of x. This is how the boundary layer essentially grows, and that this delta is actually proportional to square root of x. Okay, so this is the background behind this boundary layer analysis and all those things. And then what you also saw is that there is another approach which is a bit simpler, I would say, to Blasius's solution, because Blasius's solution involved using all those similarity variables and then solving a solving a non-linear actually. So it happens to be that the final form of the equation is a non-linear ODE. It's a non-linear third order ODE basically that you need to solve, and you cannot get analytical solutions with it. You need to solve this numerically basically. And just to bypass all these steps, there is another approach which was developed by von Karman. I think his name was Theodor von Karman. If I recollect correctly, he found out an integral approach to basically calculate the boundary layer thickness delta. And his idea is that if so, the approach that he developed, that is the von Karman model. His idea was that if you integrate the Navier-Stokes equation along the cross stream direction, then what you are actually doing is you are reducing the y dependence of the variables in a way. Okay, and then you reduce one dimension, and then what they did is so basically so we will see that very shortly, is that this also gave away, that is this momentum approach. It also that is this von Karman momentum approach. It also gave a way to evaluate this uh, boundary layer thickness delta, but this is an approximate approach. And as I said, the momentum, that is the boundary layer thickness, using the momentum approach, is a strong function of what velocity profile you choose to write your boundary layer equations. Okay, and I believe this is the idea that 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 is all behind the famous boundary layer theory. Okay, so now what we will do is we will solve a problem involving this. So we will not solve problem associated with Blasius, because these are very long problems. Exactly what the Blasius solution is, and you have already derived that in class. What we will do is we will instead use the approach developed by von Karman to do some analysis on this boundary layer, and then eventually find out what is this boundary layer thickness. So that's the idea that we will follow. Okay. All right. Uh, Before me formally introduce you to the question, if possible, I would like you to just have a quick glance at the question and try to find out what the question is actually asking us to evaluate. And of course, I will anyway discuss this. Okay, all right. So what it says is that it's just a flat plate analysis that I just now stated. It just so there is a fluid, as you can see, there is a fluid that is coming with some u infinity from the left hand side, as you can see of my screen, and then suddenly it experiences a flat plate uh, in its, let's say, downstream, or let's say in its path. And then as I say, that on account of viscosity, a thin layer of region develops, wherein the viscous effects are dominant, and that's why we call it as the viscous dominated region, or simply the viscous region. And the region outside the boundary layer, we call it as the inviscid region. And the access system is such that the coordinate horizontal to the plate is x, and the coordinate vertical to the plate is y. Okay. And what they said is that they are now asking us to assume a velocity profile in the boundary layer of this form, which is a plus by plus c by y square. This is the velocity profile they have asked us to assume. And then the first task is that they are asking us to evaluate these constants based on appropriate boundary conditions that we can apply in this boundary layer theory. Okay, that's the first task, that we need to evaluate these constants which are unknowns a, b, and c uh, by using appropriate boundary conditions on for this velocity profile. Okay, and the fact that there is a flat plate that is present here. And once we are done with evaluating these a, b's, and c's, the next task is to calculate how this. So the next task is to calculate how the boundary layer thickness varies, that is delta. So it's like how the boundary layer thickness delta of x basically varies, or they are just asking us what will be this delta of x. And what we will do is we will use, I'll write it down here, we will use momentum integral approach, that is von Karman's momentum integral approach. Okay, momentum integral approach. Okay, that's it. So I hope you understand. I hope you understood the problem. So it's just a simple flat plate problem on boundary layer analysis. There's a fluid coming with u infinity. There's a growth of this boundary layer. They said that, okay, now approximate the velocity profile of this boundary layer. So if you remember, the velocity profile will look something like this. So the velocity would be 0 here on account of something which is known as the no slip boundary condition. And in the inviscid region, the velocity will not change because viscosity is simply not present there. So the velocity here would be just u infinity. Here the velocity will be u infinity, and in this region the velocity essentially grows from 0 to infinity. In correct sense, it actually grows from 0 to 99% of u infinity. And this is what defines the boundary layer thickness delta. So delta is essentially defined as the thickness up to which you recover the lost velocity. You recover basically the 99% of the free stream velocity is what defines the boundary layer thickness. This 99% is not a magic number. It's just that it's like now you can ask me why it is 99 and why it is not 100. It's like it's again that what people say is that again the chicken and the hen problem. It's just that you cannot define, you cannot basically pinpointedly say that, okay, this is the region. Practically you cannot pinpointedly say that this is the region where I get exactly the first stream velocity. This is practically not possible. That's why people say that, okay, once you recover 99% of the free stream velocity, that's it. That's your boundary layer thickness, and that's the reason why they call it as 99% and not 100%. Okay, that's the idea. But anyways, let's first get started with calculating these constants a, b, and c. Okay, so the first task, so task 1 is to evaluate the constants a, sorry, to evaluate the constants a, b, c, and d. Okay, sorry, there are just 3 constants, so it's just a, b, c. All right, so let's do this. So what do we have? So it's a easy task, right? So you just solve one of the assignment problems which involve calculating these constants. So I have that my u, the velocity profile inside the boundary layer, is a plus by plus cy square. I just need to evaluate this a, b, and c. So we will use the boundary conditions. So since there are 3 unknowns, we at least require 3 boundary conditions. In fact, we just require 3 boundary conditions. So the first boundary condition is just trivial. So at y equal to 0, I know that my u at y equal to 0 is just 0. This is the no slip. Okay. And then if I introduce this boundary condition into this velocity profile, what do we get? So we get that u at y equal to 0 is 0, and then this just gives me a to be equals to 0. This is one unknown that we evaluate, okay, from one boundary condition. That is at on the surface of the plate, your velocity is typically equal to 0. Oops. on the surface of the plate, your velocity is typically equal to 0 because of this no slip boundary condition. All right. The second boundary condition is that at y equal to delta, what do we have? So at y equals to delta, we have u equals to u infinity. And now don't say that this is just 0.99 of u infinity. That 99% we'll just ignore here, okay? It's so in definition they say it's 99%, but for the sake of mathematics, we will say that okay, the full far field velocity is recovered at y equal to delta. And that's what we will write here, that y equal to delta, my u happens to be equal to u infinity, okay? And then if I substitute this, I'll get u infinity equals to b delta plus c delta square, okay? And okay, so this is one equations. I need to solve this. And then the third boundary condition is that at y equal to delta, you can see that after y equal to delta, there is no gradient of the velocity field, meaning that the shear stress, if we go out of this viscous region, is 0, basically. That means that the velocity gradient is 0. And this is obvious because this is an inviscid region, okay? The shear stress comes if there is a velocity gradient, which is non-zero, of course, in this region. But once we go outside the viscous region, I know that at y equal to delta, my shear stress is that my velocity gradient is basically equal to 0. Okay? So at y equal to delta, my del u by del y is equals to 0. And this will give me what? This will give me the fact that b plus 2c delta to be equals to 0. And from here, I can say that my b is equal to minus 2c delta. That is the second equation. And then, if you use equation 1 and 2, okay, if you just use, so what you need to do is just use equation 1 and 2, and it's just two unknowns and two variables because your unknowns are just b and c. The unknown variables are b and c, that is this b's and c's, and you have just this equation and this equation. That's it. Which means just do the math. I just skip the math here. It's just solving two equations for two unknowns. That's it. So if you do the math, you will see that your a indeed is 0, that we already evaluated. Your b, this comes out to be equal to minus 2 u infinity by delta, and your c, this comes out to be equal to minus u infinity by delta squared. Okay. So this is what your constants, the unknown constants, come out to be. Okay. I hope, oops. I hope you are with me on this so far. Okay. Which means once you know A, B, and C, you basically know the velocity profile, which is this. So your velocity profile, you just substitute this A, B, and C there. So your velocity profile was what? Your velocity profile was U equal to A plus BY plus CY squared. That's what was your velocity profile. Okay, and then just substitute your A. So your A is basically equals to 0, which means that you get what? You get U equals to B, which is 2U infinity. Okay. All right. So your B was 2U infinity by delta. That is what you got. This is Y plus your C is equal to minus of U infinity by delta squared. And then this is Y squared. So what you do is you take this U infinity common and then just bring here to the numerator, so to the denominator. And then you get U by U infinity as what? So you get it as 2 times of Y by delta minus Y by delta whole square. That's it. So that's your velocity profile inside the boundary layer. Okay. This is your velocity profile inside the boundary layer. So you can appreciate one thing here. See, can you tell me that whether this u, this is just a function of y or this is a function of x and y? Which one is true? Okay. think about it, because this is an important question here. It appears that your u is just a function of y, but this is not the case. The reason behind this is the fact that your delta is essentially a function of x, and that we already saw here when I explained to you how this boundary layer grow. Because we saw that when I am at a particular x, my thickness, the boundary layer thickness is some delta of x. When my x increases, my boundary layer thickness also increases, which means that my delta essentially should vary with x. This means that my delta is indeed a function of x. And from the Blasius solution, at least you can show that your delta is proportional to square root of x. And this is something that we will also show from the momentum integral approach. Okay, but in essence, it means that your delta is indeed a function of x, which means that indirectly there is an x dependency that is there in this equation, which means that your u is actually a function of x and y. And that's also the reason why you solve the 2D, Navier-Stokes equation in the Blasius approach, because your velocity in principle is a function of x and y. That's the idea. Okay. Anyways, all right. Okay, so I'll stop here for a couple of minutes, and then we'll solve the second part of this question. Okay, so in the second part, what they're asking is that once you are done evaluating this ABC, what you now need to do is you need to evaluate how your boundary layer thickness essentially varies with x. That's the thing that we are trying to seek here. Okay, so for this, as I said, what we will do is we will use the momentum integral equation for the flat plate. So this is the second part, and this I will not prove because we have already derived this in the last class. We will directly use the results of the momentum integral equation that you derive for a flat plate. Okay, so momentum, I mean, you did this proof in the theory classes. So the momentum integral equation for a flat plate is so if you recollect, it is tau w, that is the wall shear stress, by rho u infinity square, and this is equal to d theta by dx, where your theta is known as your momentum thickness. And this is one of the results of von Karman's analysis. Okay, this is one of the important results of, so I hope you can look back to your notes of the week's class and week's theory class, and then you can appreciate it. Okay, when you are doing the von Karman momentum integral analysis, oops, why is this creating so much problem today? Let's just leave it. Yeah. So the point is, this result is essentially so this relation is essentially a result of von Karman's momentum integral approach. Okay, I'll not do the proof here. You can look back in the week's theory class to get the idea of this proof. Okay, so what we now need to do is we need to evaluate this tau w, we need to evaluate this momentum thickness delta in order to get the boundary layer thickness, momentum thickness theta, in order to get the boundary layer thickness delta. Okay, so let's do it step by step. So my tau w, that is the wall shear stress, I know that this is just mu times of del u by del y evaluated at y equals to 0. That's the definition of wall shear stress. And I know that I know the velocity profile here, right? So the wall shear stress would be just del u by del y here, which means, and then you need to evaluate this at y equal to 0, which would be just 2 by delta times u infinity. That's it. Okay. So your wall shear stress is just mu times of 2 by delta times u infinity. That's obvious, right? Because you need to evaluate this del u by del y. And if you do del u by del y, you will get 2 by delta minus what? Delta square by 2y. And then if you evaluate this at y equal to 0, this term basically goes, which means that you just end up getting 2 by delta times u infinity. So your wall shear stress, tau w, is just 2 mu u infinity by delta. And remember, your wall shear stress is actually the maximum viscous stress that the fluid experiences, and this is experience at the wall basically. And then when you move when you move away from the plate, your shear stress basically decreases and it goes to oblivion when you reach the boundary layer thickness delta. When that is when you reach y equal to delta. Okay. All right. So then what we do is we substitute this wall shear stress, we substitute this value of wall shear stress here, and then what we get is 1 upon rho u infinity squared times 2 mu u infinity by delta, and then this u infinity and u infinity get cancelled, and then I have this ddx of momentum thickness, and the momentum thickness has got a definition something like this. So I think this is also something that we have derived. So I'll just use the definition here. So it is del x. So it's ddx, which is already present, times your theta, that is your momentum thickness, is essentially related to the velocity field as something like this. It is integral 0 to delta, which is of course a function of x, u by u infinity times 1 minus of u by u infinity dy. That's the definition of your momentum thickness. So that's what we will write it down here. So it is integral 0 to delta u by u infinity 1 minus of u by u infinity dy. Okay. So now all you need to do is just evaluate this integral. That's it. Because we know what is u by u infinity, because u by infinity is just 2 into y by delta minus y by delta square. So we just need to substitute it here and do the integration. So this becomes 2 times the kinematic viscosity, because I can evaluate the kinematic viscosity, because this mu by rho happens to be the kinematic viscosity. So it is just mu by rho, which is, so this dynamic viscosity by rho happens to be the kinematic viscosity, which is just 2 mu by delta u infinity, and this is equal to ddx of integral 0 to delta u by u infinity is 2 times y by delta minus y by delta squared. So it just becomes 2 times y by delta minus y by delta whole squared. Okay. And then I have 1 minus of u by u infinity, which is 1 minus 2 times y by delta plus y by delta whole squared. And then this integration is done with respect to dy. Okay, so let's first do this integration. Let's first do this integration, and I'll call this integration is as I, and then just let's find out what is I, and then we'll substitute the value of I in this ddx basically. Okay, so your integration I is integral 0 to delta. Okay, 2 times of y by delta minus y by delta whole squared. Okay, and then I have 1 minus of 2 times y by delta plus y by delta squared, and then this is dy. Okay, so for the ease of integration, what we'll do is we will do a change of variable, and we will call this y by delta as m, which means my dy is just delta dm. I hope you can understand what we are doing here. Because of the fact that your delta is just a function of x, that means if you differentiate this with respect to y, you will just have delta as constant. Okay, and then if I just substitute this change of variable in the integration, I will just get I as integral 0. So when delta is basically, when y is equals to 0, my m becomes equals to 0. That's why this is 0. When my y becomes equal to delta, my m becomes equals to 1. That's why this integral will be from 0 to 1 with respect to the new variable that we introduce. This is 2 times of m minus m squared. And then this is 1 minus of 2m plus m squared times dy is delta dm, but delta is not a function of y, so this delta will come out of the integral and this will be just dm. That's it. Now, if you do this integration, this is just a simple integration because we have just done this change of variable. So what we will see is if you do this integration, this will just come out to be equal to 2 by 15. You can check it at your end. Just multiply first these things Just multiply these things first and then just integrate this with respect to 0 and 1. So this integral I comes out to be equal to 2 delta by 15. Okay. And then if I substitute this integral here, if I substitute this if I just substitute the value here, it just comes that 2 nu by u infinity is equal to d dx of 2 by 15 delta. But remember, delta itself is a function of x. Okay. So what I can now do is I'll do one thing. All right, so let's see what I can do. Okay, so I'll write this as 2 nu by u infinity 2 by 15 d of delta, which is a function of x, by dx. And then I'll do this. So now in order to get delta, I need to integrate. But the good thing is this is of the form of variable separation. Okay. So what I will do is I will write this as 2 and yeah, remember there is this delta here also. Yeah, there is a delta here. There is a delta here. There is a delta here. So what I'll do is I'll do this variable separation where I'll just keep the delta terms together. So it becomes 2 delta d delta, which is a function of x. And then the other terms becomes 2 times of 15 times of nu by u infinity dx. And then the good thing is this 2 delta d delta, this can be written as d of delta squared. Okay. And then this can be written as 30 nu by u infinity dx. And now if I integrate it, so when x equals to 0, my delta is equals to 0. When my x is at some arbitrary length x from the leading edge, my delta is, let's say, some delta of x. So if I do this integral, this d and integration will cancel, so which means this is just going to be delta squared from the limit 0 to delta of x. Okay. And then this would be 30 nu x by u infinity. Okay. Let's just see. These are just simple algebra that we are just doing. Which means that this now becomes delta as a function of x squared is equal to 30 mu x by u infinity. Okay. And then this delta varies as square root of 30 mu x by u infinity. That's it. That's the result that the question is asking. And you can appreciate here that you can show that your delta, which is a function of x, this varies as square root of x. This is something that you can appreciate from this result. Because of the fact that your u infinity, which is the far field flow, and the kinetic viscosity, which is just a fluid property, is constant. Okay. And again, we saw that this is in accordance with Blasius's result. Okay. This is in accordance with Blasius's result. Okay, we can do one more thing here from this expression of delta of x. What I can do is I can write this delta of x as 330 nu x by u infinity. I'll multiply and divide the entire equation by x. Okay. And then if you rearrange this, what you can show is that this becomes delta as a function of x. This becomes 30 root 30. See, there is an x here and there is an x here. So this becomes x squared. When it comes out of the square root, it just becomes x. And just take all the other in the denominator. So it just becomes square root of u infinity x by nu. And you can appreciate that this u infinity x by nu is nothing but Rex. That is the Reynolds number. Which means that delta by x kind of varies as root 30 by square root of Rex. And then if you evaluate this root 30, you will see that this comes out to be around 5.48 by square root of Rex. Okay. And this is very close again to Blasius's result. Okay. So this means that your delta by x is varies as 5.48 by square root of Rex. Okay. And your Blasius's result was delta by x. This was 5 by square root of Rex. This was your Blasius's result. Okay. That is the one that uses the similarity solutions basically. And then you can see that these constants are indeed the variations that we just saw. And of course, this constant is very close with respect to the Blasius result, which means that the momentum integral works, and it is relatively very simple with respect to the Blasius's flat plate solution. Okay. All right. So that's all for today. I hope you got a good glimpse of how to basically solve the boundary layer equations using the momentum integral approach and how to basically calculate this constant. I think there is a doubt in the discussion forum on how to evaluate these constants, and I hope through these questions, if you just have a look at this question, uh, maybe in your free time you can appreciate how to basically evaluate these unknown constants A, B, and C, given that we have a velocity profile which is varying, of this form inside the boundary layer. Okay. All right. So we'll stop here for today. Uh, we in the next class we'll look into some more important aspects of boundary layer theory, and then we will go into our final topics, that is hydrodynamic instabilities. We will look into something which is known as stabilities of viscous fluids, and then that's all. That's the last part of this discussions, and we are also nearing our exams, so I think we'll not discuss much on turbulence because there is nothing much to be there's nothing much to be solved and shown for turbulent flows. It is just the understanding that you must have, and the theory classes to suffice to that aspect. Okay. So if no doubts, we will meet in the next week at the same time. Thank you very much for watching this lectures, watching this discussion series, and once again, if you have any doubt, you can post it in the discussion forum. And thank you for actively participating in the discussion forum, and in general, thank you for being in the course. Thank you. We will meet in the next week at the same time using the same link. And apologies for the brief connection error that we had. So the device on which I'm recording, it just got hanged, and I don't know what basically happened. So I need to have a restart. So when I was just doing the restart, the previous recording, I don't know if it got saved or not. But if it gets deleted, I'm very sorry. But if it got saved somewhere, I'll try to merge these two videos, these two recordings into one video, and then upload it in the course website. Okay. All right then. Thank you guys. We'll meet in the next week.